So, as a matter of fact, now that I looked back at that chart on page 244, it reminded me of something. We forgot to talk about the limited domain on this particular function here. No, I'm just going back up a little bit. I'm just going to make a little side note. Well, there should be one little side note here where n cannot equal what? -1. You knew that already because we've already talked about domain. What the textbook authors say on that chart is they say if n is -1, then you have something that's undefined here. You won't learn it until chapter 5 of the calculus book. And it deals with the natural log. And so you have a whole chapter on integrals and derivatives of natural logs for those of you taking Calc BC next year. Okay? So that's what that is all about.
Do we have to put that in our answer?
No. This is letting you know when you can't do it. You can't do it if n was -1.
What we get when n is equal to -1,
At this point, you couldn't do it. And so I'm not planning on giving you any that have that -1, but you never know. The one might pop up. I doubt it will pop up, but just in case it does. There you go. Okay. One other thing I want you to realize, and I'm going to show you a picture of something that represents what we started with. When we first started this problem, I showed you derivatives, and we found all these different derivatives that have the same derivative, but look at the original functions. They're different by a constant, right? We talked about that. What would that do to this graph if I had 3x squared and then I added 2 to it? What would happen to the original graph? That's why we learned that in Unit 6. In Unit 6 and Unit 7, we talked about horizontal and vertical shifts. That's what this is all about. So this would shift it up how many? 6. And this would shift it up. So when we're dealing with a problem, we might have several different possibilities for our integrals or our antiderivatives. We might have this as an answer or this. That's how come we have that plus c. Hang on a second. So the only real way to know what the exact integral is if we know one point on the original function. So we're going to do some problems where we actually find integrals knowing one point on the original function, and we're going to go there. Jonah has a question.
I have like a basic definition question. Like a derivative is like the function of the tangent line. What is like an integral? Or the slope of the tangent line? Like, but what is an integral in that term?
The opposite of it.
We figured that part out. We wanted to know.
So what we're saying is, here is the slope of the tangent line. This is the original function.
What's the graph of that slope?
This is the slope. This is the original graph. Right? It's okay. Okay, let's go back to physics. Let's go back to physics. Physics says this is the velocity. So we're finding the position function. We're going up a level, one notch. That's what an integral is. And later on when we do definite integrals, I'll show you what it looks like visually, what we're finding. Okay? That will be answered in your next section. So now that brings us to our next problem. We have one majorly big concept and 2 examples left, and we'll be done. If g prime of x is equal to 6x squared and g of 0 equals -1, find the original function. Find the original function if you know that the first derivative is 6x squared and you also have 1 point on the original function. You don't need the constant c anymore. You can actually figure out where that constant of c is. So I'm giving you the first derivative. Sometimes I might even give you the second derivative, and you'll have to start plugging some things to figure them out. So let's do this example. If I know what the first derivative is, and I take the integral of the first derivative with respect to x, can you do that? Why don't you tell me what it is? Wait, 2x cubed, what? No, we don't know that yet. Plus c. And I want you to write this as g of x. We know that the integral is 2x to the third plus c equals g of x. And it just so happens that I chose g of 0 here, but I could easily give you g of 1 or g of 2 or g of 3. It doesn't matter what this is. You just got, I want to say I probably shouldn't have chose g of 0 because Cody figured this out really quick. And I want him to be able to think outside the box because you won't be able to solve them all that way, Cody. So here we go. 2x to the third plus c. We all understand this. This is what we've just been doing, right? And that's the original function. Now, we have a value. When we plug in 0 into the original function, we get a value of -1. What that means is, when x is 0, the function's value will be -1. When x is 0, the value's function is equal to -1. I can change this g of x into -1. I can figure out what c is. I can figure out what that constant is if I start plugging some things in. The most common mistake that calc students do here is they forget that g of x is talking about the value. I'm going to write down here value. This is the value. This is the input. This is what our x is. Our x is our input here, and that's equal to the value. And so I change this g of x because that's the value of g of x when x is 0. So I plug that in. That's my input, and I should have this value, and I can figure out what c is now. C is going to be what? And now we can use that to plug back into our original equation and get what g of x is. G of x is now equal to 2x to the third minus 1. There is no more constant of integration because we know one value on the original function. So if I had g of 2, you'd be able to do it, or g of 3 and I knew its value, you'd be able to do that as well. Okay? How does this apply? Well, it might apply to physics. So let's do a physics problem. This is our last one that we will do. A ball is thrown. Upward. A ball is thrown upward with an initial velocity of 64 feet per second from a height of 80 feet. Find the position function and when the ball hits the ground. Use the acceleration of gravity as negative 32 feet per second squared. I'm going to let you write that down.